Okay, so now we are recording. Okay, so watch your mouth.
So shall I start then, or?
Okay, so let me, briefly introduce. So this is the last technical day of the training school. So I hope you've been enjoying it so far. I think we've had really good technical seminars so far, and I think today it's going to be not going to be at least as good as the previous ones. And yeah, Dan is local from our group. He's working on neuroscience, machine learning, but originally is a mathematician, so he's really interested in the fundamental aspects of problems in neuroscience and what's learning, cognition, etc. We've always had very interesting discussions. We've never so far managed to work together, but we've had lots of ideas and hopefully will come as well. So we're all looking forward to it. Actually, everybody has been telling me that this is really the lecture they've all been waiting for in this school. So
you have to
thanks a lot for it. I didn't say this to you.
I'm going to check the recording to make sure that's true.
A lot of pressure.
Good. All right. Well, thanks everyone. Yeah, so I'm going to be talking about spiking neural networks today. I don't know how much everyone knows about what that even means, so I'm going to assume basically nothing. I'll start with a quick outline of how I see today going, which is starting with me doing a presentation, me talking to you like a sort of lecture from 9 until 10. And I'm going to say, what is a spiking neural network? Why should I care what a spiking neural network is? And then I'll talk a bit about how we simulate spiking neural networks, and how we train spiking neural networks with a technique called surrogate gradient descent, which is a variant of gradient descent. I think it's probably more interesting and more fun, and the audience size is small enough that it makes sense. If you have any questions at any point, stop me and ask. Don't wait till the end. I think it'll work better like that. And then from 10 until 12, as I understand it, this goes on until 12, so hopefully I planned correctly. We'll actually do an exercise where you will implement a spiking neural network simulator in Python. And I've got a Colab template that you can start from. So you don't need to have anything installed. And there'll be a competition, which is basically who can make their neuron model fit some experimental data that I'll provide the best. And we have at the back on the right there 2 teaching assistants who will be around as well to help during that phase. And basically, yeah, you'll just be doing some coding, following the exercise, and they and I will walk around answering any questions that anyone might have. Yeah, so hopefully that will be interesting and fun. When I did this competition before in a class I taught last term, everyone quite enjoyed that aspect of it. And at least 2 of the groups managed to do better than I did. So we'll see if that's true today as well. All right, so here's what I hope you'll get from today's session. So spiking neural networks is a huge topic, and 3 hours is definitely not enough time to learn everything that there is to say about them. So what I'm hoping that you'll get is just a feel for why they might be interesting. And also enough of a sort of start in what they're like, just like, again, just a feel for it, that it'll give you the foundation, the base to start going and learning more if you want to. And I won't be offended if you don't want to, that's fine as well. I'll give you some pointers towards some more free resources that you can learn more as well if you want. In particular, I'll put this URL up again later. The course I taught last term was called Neuroscience for Machine Learners and covers a lot of this material in a lot more depth. It's all on YouTube and with Colab notebooks and stuff like that, so you can go and check that out if you wish. Right. Yes, and lots of extra reading materials if you want as well. Okay, so let's kick off then. So what is a spiking neural network and why should I care? Now, I think if I remember right, I've got quite a lot of slides today, so I'm going to go fairly quickly. So do stop me if I'm going too fast. So, all right, let's start with what is a spiking neural network? So let's start from the very basics. What is a neuron? A neuron is a cell in the brain, and it looks something like this. I've got some more realistic pictures later. But basically, it consists of a cell body These sort of projections out here are called dendrites. The dendrites we normally think of as receiving inputs from other neurons. And then they have outputs, which is here, this axon. So messages get sent along this axon. They cross from one neuron to the other by something called a synapse. And then here's another cell, that's the receiving cell. And the message that they send is very simple. The only thing that they can send is something called an action potential. It's an all or nothing signal. It basically says something happened. And it's a binary signal, it's a 0 or 1. Most of the time it's 0, and occasionally you'll get this 1 coming in. But that happens with a particular time, right? So there's various ways you can encode information in that. You can send more of these signals, so that's what we call the firing rate. That means that lots of stuff is happening, or you can use the timing, right? So you could say send 2 of these pulses with a different time between them, for example. That would be another way you can encode information. And obviously those are connected. Right, if you send at a higher rate, the time between them will be smaller, and so on. Okay, so that's broadly how it works in the brain. Of course, there's a lot more details, but that gives you a feel for it. And all of this is a sort of electrical activity in the sense that I'll talk about in a little bit more. But essentially, if you stick an electrode in here, into this cell, and record what happens to the potential difference between the inside of the cell and the outside, that's this thing called the membrane potential, you get a picture that looks something like this. And it's quite noisy. So some of that is just sort of random fluctuation noise. Some is because the cell is actually doing stuff, it's receiving inputs and stuff is happening, and this is quite a fast time scale. But every now and again you see these huge peaks where the activity suddenly goes really high. And if you zoom in on that, it looks something like this. So it's going along quite happily, and then suddenly it jumps up very high, then jumps down low, and then goes back to sort of what it was doing. And for this reason, that these plots look like this, with this sort of noisy activity and then spikes of activity, these action potentials, this message traveling along here, is sometimes called a spike. And it's just because in this picture it looks like little spikes. So I'll use action potentials and spikes interchangeably. That's the spike in spiking neuron. Okay, so we know what spike means, we know what neuron means, and I'm going to assume you all know what that means. All right. All right, so here's some nice pictures of the sort of diversity of different neurons. So these are all sort of reconstructed morphologies of neurons. So you can see the dendritic structure and the axonal structure. This is a bit like the one that we just saw, but then there's all these other sorts here in different areas of the brain, in different species. There's hundreds and hundreds of these different types of neurons. And I sometimes say that they're like snowflakes, that no 2 neurons are the same. All right, and why are they interesting? Okay, I'm going to try and persuade you over the next few slides that you should be interested in these. Whether or not I'm successful, we shall see. So the first reason they might be interesting is that we can take inspiration from biology. Here's the argument. So we're interested in engineering intelligent systems, and we only know of one system that has the sort of intelligence we're interested in. That's the brain. And the brain uses spiking neural networks, and therefore we should also be interested in spiking neural networks. Now, logically speaking, that's not an entirely conclusive argument. And it could be that we can design intelligent systems based on entirely different principles from those that the brain is using. Indeed, we seem to be realizing quite considerable success in that with machine learning at the moment. And for example, planes take some inspiration from biology, but the wings don't flap, right? We didn't do the Da Vinci's design. That didn't work out in the end. But I still think it's not a bad idea. And if you look at the history of machine learning, a lot of it is deeply intertwined with neuroscience. In fact, from the very earliest sort of people who kicked off the field of machine learning didn't think of themselves as different from neuroscientists. They were the same people. They were thinking, what was the brain like? If you go back to like McCulloch and Pitts, the first neuron model that sort of started machine learning in some way, they describe it as a model of the brain, right? And that's true of a lot of that early history. All right. Single neurons can actually be quite powerful, much more powerful than in machine learning. For example, there's a recent paper that showed that a detailed model of a single neuron is enough to solve M-ness on its own, like one neuron. So in principle, these can be quite a lot more powerful than the neurons that we think of in machine learning. I mean, funnily enough, the way they did this was they showed that it was equivalent to a small neural network, and that neural network can solve any statistical. Anyway. But all right, so next reason why they might be interesting is power efficiency. So, so this is a sort of fairly typical GPU drawing 6,500 watts, quite a lot of power, and I guess you all know probably better than I do how much the power usage of machine learning is causing problems now. The brain is estimated to use less than 20 watts. In fact, actually, that's an old figure. I think the latest thinking is that it might be more like 6 watts, actually. Or you can take the brain of a bee, which is 10 microwatts. And it has been claimed that the current machine learning is probably more along the capacities of the bee brain than the human brain. I mean, bees can do some really sophisticated stuff. They can recognize stimuli, they can engage in social activities, they can understand what's going on. So we got 6,500 watts versus 10 microwatts. So you can take these sort of brain-inspired principles and build hardware that uses them. So an example of this from 2008, there's more recent stuff, but there's a nice picture of this one, so I used that, is this IBM Synapse chip, which runs spiking neural networks in a way that the hardware is designed to match what those spiking neural networks do. So you're not running it on a GPU or a CPU, it's a specific hardware for this specific type of algorithm. And this thing used 70 milliwatts. And it's a bit old, it's 2008, but it did, I think it was running a video analysis on 320 by 240 pixel video. And when doing that task, it ran on 70 milliwatts. So it's really like a huge leap in terms of power efficiency, if you can get it to work. Yeah, so from the point of power efficiency, spiking neural networks have a really incredible potential, but we do need better hardware, and perhaps even more important than better hardware, we need better algorithms. We don't know how to build spiking neural networks that perform as well as artificial neural networks from machine learning. So this remains potential for the moment, and that's why I guess not everyone is doing it. All right. Any questions so far before I move on to the next bit? No? Good. All right, so I'm going to talk a bit more mathematical detail now about how we model and then simulate these spiking neural networks. So let's go back to our neuron. I think I described most of this already actually earlier, so I won't go cover this again. And there's our trace of the electrical activity. Now, I said that this was electrical activity. And specifically, we measure this thing as the difference between the potential difference inside and outside of the cell. And that's also how these things operate. I'm not going to talk through a lot of detail about this, but the membrane, the cell membrane, is a semi-permeable membrane. And the way that electrical activity moves around these things is essentially caused by having these things which are called gates, which you can kind of think of them as like little holes that open and close depending on the conditions around them. And they allow selectively specific ions to come in or out. So the main ones are potassium and sodium. So depending on the general electrical and chemical activity around them, they'll either open or close, and that potassium and sodium go in and out, and that creates a potential difference between the inside and the outside of the cell. And when the neuron chooses to fire a spike, a cascade of these opening and closing runs along this axon until it gets to the synapse. I won't talk about what happens at the synapse, that's even more complicated. Yeah, anyway, I don't want to say too much about the biology. If you're interested in that, you can have a look at my course where you go into it in a bit more detail. But yeah, so it's maybe nice to just have a little picture of that in your head as we go. And the spike looks something like this. I won't talk through this all in detail, but basically what happens is when the potential difference gets to something called the threshold, it starts a chain reaction of events that causes the membrane potential to leap up very high, And then as the balance of the different sodium and potassium and some other chemicals reaches a certain point, it flips, and it will suddenly, the potential difference will gradually drop again, and then it will sort of return to its sort of baseline activity. So the key thing to know from all of this is that there's this key threshold, that if the potential gets to the threshold, you will get a spike. And not only that, but this spike is entirely stereotyped. Once the spike starts, it always looks basically exactly the same, always has the same shape. Yeah. All right. So now, before we talk about modeling spiking neurons, let's just quickly recap how we model artificial neurons, because a lot of it is the same. You probably know this sort of picture. You have an artificial neuron which you model as having some set of inputs. Each of those inputs has a weight attached to it. You sum the input multiplied by the weight. You pass it through some nonlinear function f, and that's the output of the neuron, right? That's sort of fairly classic here. And that function, that nonlinear function f, could be a sigmoid function, it could be a Relu function. Different things can be used. Many different things work. So actually, it's actually quite a good model of the brain, of neurons in the brain. And you can actually ask the question, well, what is the correct activation function if you wanted to do something like the brain? And it's something we don't still quite have the right answer to, but the latest paper I found on this from last year says it's some function that looks a little bit like this. So it's a little bit sigmoidy and a little bit Relu, but not quite either of them. I think when I looked at this paper, it hadn't yet been peer reviewed, so I can't tell you that this is definitely the correct one. So, that seems to be the latest sort of picture. Okay, so now let's talk about biological neuron. This is a neuron model rather than an actual recording, but I'm going to use this to talk through what happens, the different steps that we need to model to model a biological neuron. So this is the membrane potential of its neuron over time as it leads to it spiking, resetting, and receiving significance. So what happens is when a spike arrives at this neuron from the dendrites, it happens at these times with these little red circles. And what happens is you see a slow increase followed by a decay in the membrane potential. So each of these input spikes causes a sort of the addition of this shape, sort of kernel essentially, added to its membrane potential. And then if you get multiple of them in sufficiently small amount of time, they add up to enough to reach the threshold of this neuron, which in this case is minus 60 millivolts, causes it to fire a spike. After the spike, it resets and goes back to its previous activity. Yeah, okay, so that's roughly the picture we should have in our mind about all of these models. They're all going to have roughly the same broad picture. Okay, so I'm going to keep that on the screen while we talk through some of the mathematical details. So let's start with the simplest possible model that we could have of that process, which is called the integrate and fire neuron. So in the integrate and fire neuron, we just model it by having some membrane potential value V. In this case, I've thrown away the units, so it's just going from 0 to 1. Each time a spike comes in, the V is increased by some fixed amount, and nothing else happens, right? So we forget about this sort of shape. We just have it as increasing by some fixed amount each time a spike comes in. When it hits the threshold, we fire a spike and reset it back to its original value. That's called the integrate and fire neuron. Here's how we model that. We have a variable V, and when an incoming spike, let's give it an index I, arrives, we increase V by Wi, the weight attached to that incoming spike. And then we have a threshold condition, which is that we fire a spike whenever V goes greater than 1, and a reset event after the spike, set V equal to 0. Okay, so that's the complete sort of mathematical specification of this, and I can imagine that you can sort of imagine that this is not too difficult to write a simulation for, right? There's nothing very complicated going on. Okay, so the next step up in complexity is that we noticed that actually there's a bit of decay after this initial fast increase. It sort of seems to start decaying back to 0. Now, the way we model this is with this differential equation. So in the absence of a spike, the membrane potential will evolve over time according to this differential equation. And for those with a sort of physics or electrical engineering background, this is basically saying that the membrane is acting as a capacitor, and that is indeed electrically more or less what the membrane is doing. So that's where that comes from. And the solution to this differential equation, in the absence of any further incoming spikes, is that the activity decays exponentially with a time constant, which is this time constant tau. Okay, so let's draw a picture of that. So now we have the same as before. An incoming spike causes this instantaneous jump, but then in between the spikes we have this exponential decay again. So jump, exponential decay, still enough eventually to push it over the threshold, fire a spike, reset, jump, exponential decay, and so on. Okay. All right, so now to simulate this, it's obviously now a little bit more difficult because we have to start thinking about solving this differential equation or inserting a solution or something like that. There's various ways that you can approach that. Okay, and now the next thing that we didn't talk about is this shape, right? It doesn't just instantaneously jump and then decay. There's a sort of slow rise before the decay happens. And we can model that by introducing an extra variable. In this case, it's an input current. And we say that the input current has the shape that we had before. It has this instantaneous jump and then starts to decay, instantaneous jump starts to decay. And that input current, so now the spike has an effect on the variable I instead of V. That I variable decays exponentially. And now the same equation for the membrane potential holds as before, but now we also have this, this input drive coming from I, with some resistance there as well. Okay. And with that, you get a picture that's like this, right? So now V doesn't suddenly instantly jump, V increases and then starts to decay a bit. Actually, this picture doesn't quite show the decay part of this, but you get a picture that's more or less like this. Right. And I should say at this point that you don't necessarily need all of these details. And there's a lot more detail that you can put into these models. I just want to try and give you a feel for some of the details you can or cannot choose to include in these models, depending on what you want to do with. Some of them may be important, some of them may not. Okay, so all right, so I think I'm just going to talk about one more detail we can include in these models, which is spike frequency adaptation. So let's suppose we've got one of these neurons, and there's a constant, regular pulse coming in, right? Every, I don't know, whatever that is, like every few milliseconds, a spike comes in. This is what would happen. You jump, starts to decay, jump, starts to decay, you'd reach the threshold, you'd fire a spike, you reset, and then you do exactly the same thing. If it's a regular series of pulses, each of these little windows looks exactly the same, and the output will therefore be entirely regular. But that's not what real neurons do. If you put a regular input into a neuron, you get the time between spikes starts to get longer and longer, right? So the time between these first two spikes here is much shorter than the time between these two spikes here. And there's different sorts of adaptation you see. There are some neurons that will only fire a single spike at the beginning of a regular pulse, a regular train of spikes, those onset cells. There are some that will do what I've shown here, which is that the spacing between the outputs will get longer and longer. There's some that might fire a burst at the beginning and then stop. There's some that will only fire when the input switches off. There's all sorts of different sort of behaviors that you can get. So here's how we can model that. There's many, here's one way of modeling that. There's many, many different ways. This only captures one aspect of it. And it's actually, I should say, this particular one is not particularly biologically realistic, but it's just the simplest possible thing that gives that sort of behavior that you can come up with. In this case, we do an adaptive threshold. So the idea here is that this threshold before was this fixed number 1, right? You hit this threshold, you fire a spike. Now what we say is each time you hit the threshold, you increase the threshold. The next spike is more difficult to attain, but that there's some recovery over time. So if you, for a long period of time, you don't have any spikes, that threshold will start to go back to its original value of 1. And with that, you can see that because each time you fire a spike, the threshold gets a little bit higher. You can see that the gap between these outputs starts getting longer and longer. And you can also see that depending on the parameters you put into this, you could imagine that eventually it might get to the point where you stopped firing a spike for a little while because you just couldn't quite reach where the threshold had got to, for example. So you can implement quite a few of these behaviors with different parameters. And in terms of the maths, we model it in the same sort of way, right? We introduce a new variable vt, which is a threshold, and it decays back to the value 1 with some type of constant. Is that okay? Is the meeting still working? Something just popped up. No, it's fine. So it decays back to its resting value with some type of constant. After a spike, as well as setting the v value to 0, you increase the vt by some fixed constant, right? That's this jump here. And your threshold condition, instead of being that v has to be bigger than 1, is that v has to be bigger than this vt. So again, we can always write the equations in this sort of standard sort of tabulated form. Okay. All right, so I'm almost done with this section. I'm just going to briefly preview what's going to be in the exercise. So it's going to look basically something like this. If you open up the Colab notebook, you'll see that there's a template that has a few different functions that look something like this, right? It's a leaky integrating fire neuron with some constants, an input current. I've started writing a little bit of the code to sort of give you an indication, but then there's this comment here that says fill in the gaps here, and then what you have to return is the output membrane potential and the array of spike times. Okay, and so the exercise will be to write the code that should go here. And then there's a little test suite that will take your function and plot a figure based on a particular input. And if you get it right, it should look like this. And this is included in the notebook. So basically, your task is to fill in the gaps here so that it produces this figure. So this is just some particular input when it should spike based on. Having got that to work, then there's this the competition of fitting the model to the experimental data. And the experimental data comes from a competition that was ran maybe around 2008, something like that, where they put an electrode into a neuron, and they would inject, rather than record the current, they would inject a current into that neuron, and that's these orange lines here. And these were just like random walk currents, just to give some interesting input to the neuron. And then they would also record the output of the neuron, which is this blue, right? So if you put the orange current into this neuron, into this real neuron, you get this blue output from it. So basically the task is, can you come up with a neuron model that, given the orange curves, returns the blue curves, right? It's a model fitting problem. And just as an example, I start you off with a simple leaky integrating fire neuron with just a couple of constants that I just picked out in my head, gives spike trains like this. So if I remember right, yeah, the data is these orange blobs. That's when they spiked, right? So this says that on this particular neuron or this particular input current, it fires a spike at this time with the associated current. And the blue ones are what the model is producing. So you can see that there's some sort of match, right? Like the blue dots are somehow in the same area where the orange dots are, but it's not terribly good. So you can do a lot better than this. And it has a metric built into this test suite, which will give you a number, which is basically how good your fit is. You want that number to be as low as possible. And yeah, we'll see if you can come up with the best fit to that. And you can use whatever tools you know of to do that. Do it by hand if you want, you know, throw it into some global optimizer, come up with something cleverer than that if you want. So, all right, so I threw quite a lot of maths at you there. So is there any questions before I move on to the next bit? It's slightly different. And it would be good to understand what came so far before we move on to the next bit.
So the important thing is that the spike is going to be above the threshold.
That's
so the amplitude is not that important for the information, I mean, for the data that you have to encode into the spike.
Sorry.
So the important thing is that, as you mentioned in the last slide, so when you have the data, meaning that you have to go above the threshold for the spike.
Yeah.
But how much is not? So it's not in the amplitude of the spike, the information.
No, so the spike has no, the amplitude of the spike actually carries no information. Like if you record them, you do see slight variations in the amplitude, but that doesn't actually change anything, as far as we know. To the best of our knowledge, that doesn't change anything. But I should add, when I say broad statements about things in neuroscience, all of them are slightly untrue, because what we always find in neuroscience is that anything we think we know has some weird exception. So there's always an exception. But yeah, mostly it doesn't make any difference, the amplitude. And all that matters is yeah. Basically, what happens is that all of these processes basically start these cascades. And once the cascade starts, they follow the same time course. So when the spike sort of arrives at the synapse, it causes a sort of cascade of activity to happen at the synapse. It doesn't make any difference how big that amplitude was, essentially. So it really is this binary all or nothing. Yeah.
Sorry. In some slides before, you mentioned that the time between the spikes is increasing. That is next to please explain that again.
So here the incoming spikes are coming at a regular time, but once we put this threshold in, it takes more of those spikes to get to the threshold once the threshold has gone up. Right, so now the time between this spike and this spike, this input spike and this output, sorry, this output spike and this output spike, is shorter than the time between this output spike and this output spike, because it always goes back to 0. So to get to that threshold takes more incoming spikes, basically. Yeah. All right. So now let's get on to how we can actually train these networks to do something interesting, right? Because that's ultimately what we want to do if we're thinking about machine learning applications. It's also ultimately what the brain wants to do, so it's also of interest for neuroscientists. So what do we know about how spiky neural networks learn? Well, the short answer is we don't know. There's so much we don't know. There's a very few things that we know about how real neurons learn, but mostly I would say the answer is we don't know. We can break that down into two slightly separate questions, which is how do biological neurons learn, and how can we train our network models, our spiky neural network models, to do tasks? And there might be relationships between these, and I'm not going to talk in this tutorial at all about the question of how biological neurons learn, but only focus on how we can train our models to do tasks. Except I will say one thing, which is that we do know that biological neurons only use local information, right? You can't pass gradients that take the entire brain state to a neuron. There's no way that information could somehow be transmitted to a neuron. All it can use is the activity that's happening nearby to it, just purely from a physical point of view. And that's really interesting because that is likely, first of all, we don't, that's challenging in machine learning as well. Local learning is a really challenge, to achieve good performance using local learning in a machine learning setting is also really difficult. The brain seems to have a really good solution for that. And it's also likely to be useful for sort of both power and data efficient learning. So a lot of this hardware that I was talking about, this neuromorphic hardware, a lot of it is based around this idea of in-memory compute. I don't know if everyone's come across that, but the idea that if you do computation and you keep your memory and your computation somehow in the same physical space, you have lower power because essentially you're not sending messages, you're introducing bottlenecks, and so on and so forth, right? The brain seems to do that really, really well. A lot of this hardware is designed around the principle of doing in-memory compute. It would be really nice to know how the brain is doing so well at in-memory compute and how it's able to train and learn and everything so that we could adapt that to non-biological settings. But like I said, I don't have answers for that for you today. But it is a major topic in neuroscience, and I also guess in machine learning as well. All right, so first idea that you might have, if you come from knowing some stuff about machine learning, is why don't we just do gradient descent? So I'll just very quickly recap this. It's probably familiar to everyone, but I'll just give my way of thinking about it. So we're writing the neural network as some function. Y is f of x theta, where x is the inputs, y is your outputs, and theta is some vector of parameters. For example, theta could be a weight matrix, and your function could be multiply the weight matrix into the input vector and pass it through some nonlinear function, for example, a sigmoid. We want to minimize some loss function, right? So we have a desired output y star, our actual output y, and then we want to pick the parameters that minimize this loss function. And the way we do that is by using some form of gradient descent. In other words, each iteration, we update the parameters in the direction of the gradient of this loss function. Okay, and we can compute this gradient by using essentially the vector chain. I won't talk about that, but like that's how that vector chain rule comes out. And the point is that this is just a bunch of matrix vector multiplications in the end. Okay, so how about let's just do this, but now our function f here is the function that we get from a spiking neural network rather than just a simple nonlinear sigmoid or whatever, right? Why doesn't that work? So it doesn't work, and I'll explain why. Here, just as a reminder, this is the condition, this is the equations defining the leaky integrating fine neuron that we saw earlier. I'm just going to rewrite this slightly, and I'm going to remove synapses for the moment, just to simplify the presentation of the problem. We don't need to think about synapses to understand why we can't do this. So the threshold operation, which over here is written as v is greater than 1, I'm going to write like this. S of t is the Heaviside function of v of t minus 1. Right, the Heaviside function is this function that is 0 when x is less than 0, and 1 if x is greater than 0. So S will be 0 if v is below the threshold, and 1 if v is above the threshold. Now we can think about updating the solution as we go from time t to time t plus delta t by an equation that's something like this, right? V at time t plus delta t, well, you've got this exponential decay, e to the minus delta t over tau times the value at time t. But then we also have to multiply by whether or not we spiked. So if we had spiked at time t, then s of t will be equal to 1. So this multiplied by 1 minus s of t will give us a 0 in the output. So it resets to 0 after firing a spike. Whereas if v of t was less than the threshold, s of t will be 0, and this multiplication will just do that. Right? So that's a way we can encode this reset, this threshold, and this update all into these two equations. So at this point, you can say, okay, right, so now right, we've got our f function, we can compute our loss, we can compute the gradients, we can use the chain rule, blah, blah, except everything about that is fine, except for this one function h, which is going to cause us problems, because the differential of h is, well, it's undefined when x is 0, but more to the point, it's 0 almost everywhere. So for all possible values, except for 0, this gradient is 0. So basically what happens when we compute these derivatives is that the derivative is 0 almost everywhere, and we wouldn't actually ever move in this weight space at all. So yeah, so gradients are 0 almost everywhere, and so gradient descent doesn't work for spiking neural networks. Do you mind shutting the door, just because I think there's people coming up that lecture. Yeah, okay. So, all right, so gradient descent doesn't work, but it turns out that there's a trick. And that trick is what's called, hang on, I think, when did this, I think this dates from around 2018, something like that. Someone came up with this, I'm not exactly sure of the exact date, but fairly recent trick, which is called the surrogate gradient. So, as I said, we've got this problem that this derivative is 0 almost everywhere. The solution is a little bit strange, which is that we replace this, we pretend when we're computing gradients that this derivative isn't 0, but is in fact the derivative of a smoothed version of the Heaviside function, right? So this is what the Heaviside function looks like. We can do a smoothed version of it, and this thing will have gradients that are well defined everywhere. And what we do is we just say, whenever you see a dh by dx in this computation, replace it with the dh smoothed by dx, right? Now this seems like a very weird thing to do, because essentially you're saying we're going to try and optimize some function by using the gradients from a different function. Right? This different function is called the surrogate. A priori, there's no reason why that should work, although there's some intuition I can give as to why it does work, but it does work, which I'll show in just a second. And that intuition is maybe something a bit like this. So I made this a bit small, but hopefully you can see. So if the true like lost landscape looks something like this, right? The problem we have is that this thing is flat everywhere except for these jumps, right? So the derivatives are 0 almost everywhere, and you can't move around. By using the surrogate function, it makes the loss function be like some sort of smoothed version of this, so that we can actually move around this landscape. But we're still optimizing the gray for the gray function, the actual thing using the non-differential h. But we're following these curves. That's a sort of some sort of intuition. I have not seen this be mathematically formalized anywhere. To my knowledge, it hasn't been. If you have an idea as to how to do it, please tell me, and then we can write a paper together. Yeah, but it does seem to. So as an example, people often smooth using like a logistic function. If we smooth with this logistic function, it's got a nice, the derivative has a nice form, it's quite easy to calculate. And it's all built into PyTorch, which is maybe why everyone does it. But it actually doesn't really matter what function you use. So this guy, Friedman Zenker, is the one who came up with this technique. And he tried out a bunch of different functions. And basically, the thing learns no matter what function you use in here. In fact, you can replace this with a piecewise linear approximation, where the smoothing is just to slightly change this from being infinitely steep to being a little straight line segment here. That works as well. All sorts of things work. Yeah.
So in normal machine learning, if you want to learn something in quantization, it's pretty much the same. So the same thing arises. So you can expect
they use these surrogates as well. Is there a theoretical reason why it should work, or I don't remember ever seeing it, but I would be very interested.
I don't see anything using
Yeah. I mean, surrogates are used in other areas, and there is mathematical justification for why they should work. You can sometimes do proofs that, you know, it's like it bounds the error or something like that, yeah, right? But
I mean, intuitively, just close enough, it should.
Yeah, right. But yep. Yeah, I think you can use various different functions. I mean, yeah, so yeah, you can't replace the function in the original thing, because then it's not a spiking neural network anymore. It doesn't have this unique property that there's all or nothing transmission of information only at the time of the spike. Right? That requires this discontinuity to be there. So if you just try to replace, I mean, that was actually the first thing people tried, and it sort of kind of worked, but the output wasn't a spiking neural network anymore, because you're essentially then sending graded information, like, you know, continuous valued information rather than discrete all or nothing information. And you lose the benefits, for example, the power benefits of only sending information when there is a threshold crossing. So you do need to somehow really deal with this discontinuity. You can't just, you know, pretend it's not there. Well, I mean, you can pretend it's not there when you're producing the gradient, but you can't pretend it's not there in the sort of forward paths, otherwise you don't get the functions. I can talk more about that with your options if you're interested. Okay. Any other questions? All right. So if we're simulating these things, the way we do it is the same as when we're doing a recurrent neural network. We essentially unroll this thing. So let's set it up like this. We have these parameters theta. We have an input at x at time t. We have some network state, which is h at time t, and h at time t changes h at time t plus 1, and so on. And then some output y at time t, some loss L at time t. And we get some idea of the dependencies by unrolling this thing. Right? So time t equals 0, here's your input, your network state, your output, and your loss. And the input at time t equals 0 will affect this, which will affect this, which will affect this. And the h at time t will affect h at time t plus 1, and so on. Right? So this is the sort of like the dependency graph of this. And you can think essentially, if your network is some function like this, So h of time t depends on h of time t plus t minus 1 and x of time t, some function f theta. And you can just start unrolling this, right? So h of time 1, h of time 2, and so on. And then you get your final output y of time t. And this basically, this gives you a very complicated function, but it's still just a complicated function of values, theta and x0, x1, and so on. So, so the point is that that's how we can then apply these gradients and so on. Right? So that's how you do it in a recurrent neural network. That's also how we do it in a spiking neural network. And obviously that is very difficult to do in practice if you try to do it by hand. Fortunately, we have PyTorch and a bunch of other machine learning toolboxes which will do all of this differentiation for us. All we have to do is write this forward pass, and it will do all of this. And that's backpropagation through time. So that's basically built into PyTorch and a bunch of other tools, and it just works. And we do the same thing in spiking neural networks. So that was my key point here, is that this is exactly the same as a recurrent neural network in that sense. All right, so there is one unique thing about how we implement these things in PyTorch, which is that we have to use the gradients of a different function. So that isn't going to work with PyTorch's auto differentiation package, because it's going to use the gradient of the actual function, which is going to be 0, the sunny side will be 0 everywhere. But actually they make it easy. So I'll just show you what it looks like in PyTorch. What we do is we create a new Heaviside function, which I've just called surrogate Heaviside here. We derive this as a class from this torch function class. And we have to implement a couple of methods. So there's a forward method, and the forward method is basically what happens when you are computing on the forward pass of these iterations. And for that, we just use the standard built-in Heaviside, right? We don't do anything special in the forward pass. But this is the neat thing about PyTorch, is that it lets you also override specifically just the backward pass of this function. Right? Give a different gradient. And so what we do then is we just, instead of returning zeros everywhere, which will be the direction of this, we basically compute the gradient of one of these sigmoid functions and return that instead. And we just set surrogate Heaviside to be the apply method of this class, and if we now use the surrogate Heaviside wherever we would have used Heaviside, it will now have these properties. And that's it. That's basically the full implementation of this surrogate gradient idea using PyTorch. I think it's brilliant how simple that makes it. Okay, and it works. So as an example, here is a data set which was designed specifically to test these spiking neural networks. It's from a data set called the Spiking Heidelberg Digits dataset. It's a bunch of people reading out digits 0 through 9 in English and in German. They recorded the audio of these. They passed this audio through a model of the first layer of neurons in the auditory system, and that produces these spikes. So the way to read these plots is that the x-axis is time, the y-axis is like the neuron index, and then each dot is a spike for that neuron at that time. And in this case, they've arranged the neurons in order of the frequency that they respond best to. Right, so this kind of looks like a spectrogram of the sound. If you've seen spectrograms of speech, they kind of look like colored versions of this. Yeah. So that's the input, and the problem is to identify which digit was being spoken just from these spike patterns. Here's just a couple of examples of what the intermediate hidden neurons in a very simple. So I think if I remember right, so what I'm showing you from here is from a model where they just take these as inputs, they feed it into a recurrently connected pool of 300 spiking neurons, and then that feeds out into a pool of 10 or 20 neurons that are essentially the readout that you get the class from. And this is just an example of some of the intermediate spike trains from that hidden layer pool of neurons. Right, it's a very simple network, but even that very simple network is able to train. And in this case, for this neuron, with just 300 neurons, it gets a test accuracy of 70% on this task, which is quite reasonable. As you can see, it's overfitting a bit there. But people have done much better than this, and the person who came up with this data set has a table on the dataset's website giving the current best known performance on this dataset, which I believe is still this one, which is around 95%, with using a few extra tricks. So it's a nice little sort of spiking specific dataset. Yeah, okay, so it works. And it's not just for this task that it works. You can throw visual tasks, video tasks, everything I've ever thrown at it, it learns. Yeah. What are some issues? So one of the big issues is that it's very resource hungry. So to say a little bit more about why, let's say n is the number of neurons and t is the number of time steps. Now, just to give an example of why t is going to be kind of critical here, is that typically with a recurrent neural network, you might consider running it like 5 or 10 iterations. If you want to do a spiking neural network, you have to simulate at the time step where the timing of spikes of that time step carries meaningful information. So that's probably around the order of about 0.1 milliseconds, right? The timing differences of about 0.1 milliseconds seem to make a difference. Certainly 1 millisecond, those timing differences make a difference to the function of these networks. But let's say you want to simulate a single second of simulated time, and you're using a 1 millisecond time step. That means that you're thinking about 1,000 iterations rather than like 5 or 10 iterations. So the number of time steps typically is very large. The amount of computation per time step is O(n)² squared. That's okay. We can throw a lot of compute power, and that's not a problem. The real problem is that we require amount of storage space that's proportional to the number of time steps. So let's say you've got 1,000 neurons and 1,000 time steps. Your storage space is going to be of the order of 1 million. You can see that very quickly it becomes unfeasible to simulate large networks for long periods of time because you're multiplying these two quantities together, essentially. And in practice, that means that, to my knowledge, the largest simulations that have been done with these spiking neural networks using this gradient descent technique have been around 10,000 neurons, which again, if you're coming from machine learning, seems pitifully small. This does not scale well at all. And this is the major problem that I think we have in training spiking neural networks, is that we just, for the moment, we don't know how to scale them well at all. They're also hard to initialize well. You need some initial state that has a reasonable number of spikes at every layer. You have to have gradients that don't vanish or explode. And that actually turns out to be a lot trickier for spiking neural networks than for artificial neural networks. There are some ideas out there, including one from one of my PhD students, but there's more work to be done on that. Also, this thing uses non-local information, and ideally we would like to have a version that only uses local information, both because that would be a better model for the brain, and also it might alleviate some of these sorts of problems as well. All right, so that's done for the my timing is impeccable. All right, so I'll just talk a little bit about some sort of prospects for the future. There's a lot of work still to be done. There's lots of low-hanging fruit and possible sort of questions and projects you could work on in this area. Obvious one being, can we make this more faster, local learning version, better scaling, make it work better with sparse connectivity. Sparse connectivity is one of those things that's started to come up more recently in machine learning, but still often connectivity is relatively dense in machine learning settings because that makes optimal use of the hardware that we have. It would be interesting to have hardware that can make better use of sparse connectivity, because in the brain, connectivity is very sparse, and if you're thinking about scaling to very large, you're probably interested in sparse connectivity. I think one of the topics that concerns me is, are there computational advantages to using spiking neurons rather than artificial neurons? Some of the things that I have in mind are that they might be useful for fast decision making. They might be a bit more noise robust, partly because of these thresholding operations and things like that. Some people have suggested that they will be more robust to adversarial attacks. that they might be more generalizable. I think at some level, this might be slightly wishful thinking in the sense that we know that the brain is more generalizable, and therefore we would hope that spiking neurons are. But I'm not sure that there's any real substantial reasoning behind that other than the hope based on what the brain is doing. I kind of think that this is slightly magical thinking. They're hoping to get something from nothing, that we're actually going to have a problem to solve. But anyway, it has been suggested, so I should, for the sake of honesty, mention it. And obviously the big one here is low power, and that's the promise of neuromorphic computing. The new research funding agency in the UK, ARIA, is throwing right now, it's 40 million projects to do with low power neuromorphic computing. It's a big topic. Big companies are doing it. Like Intel's throwing a lot of money at this. Other companies are throwing lots of money at this. So I think the low power thing is what gets getting a lot of people excited. And we can also use it to answer biological questions like what's the role of spikes? Is it just this energy efficiency? Is there something else? There's a lot of questions, as I keep saying, about local learning rules. Okay, I think that gives you some of the idea of some of the interesting things that are going on in the space of spiking neural networks. Yeah. All right. So I'm going to finish by, I'll leave this on the screen, giving some links and the links to the exercise in particular, and we can get started. So start by going to this website, neuro4ml.github.io, and for the remainder of today, what we'll do is go through the week 1 neurons exercise. So if you scroll down until you see week 1 neurons, and then you click this button here, open the ProLab, it'll open the exercise. The exercise has instructions for you to work through. I think it might be interesting to work in small groups rather than individually, so maybe have little groups of 2 or 3 or whatever you want to work on this. And yeah, and Yang and Greta at the back here will also be around, as well as I will, until 12 to answer any questions. Oh yeah, and once you get a score for the competition part, the last end of the notebook, tell me, and I'll put it up on a whiteboard or something, and we'll see who manages to do that. So you can come up with a fun team name for yourself as well if you want.
I have like a general question. Everything which we can see is about signal and signal. Is there a frequency equivalent?
So the spiking neural networks always operate in time. So frequency comes in, for example, in the auditory system, but it comes in because the cochlea is essentially acts as a sort of multi-channel bandpass filter, right? So it filters out particular frequencies. Is that what you mean? Or?
I mean, maybe, I don't know, the idea of switching time between the two domains could be useful. Maybe some operations are cheaper, let's say, in frequency levels. So maybe.
It's an interesting idea. I haven't thought about it. That could be quite interesting. Yeah, I don't have a good quick response to that.
So
it sounds like
there's something on the literature.
It's not something I've seen, but yeah, I wouldn't be surprised if someone has thought about it. But it doesn't. It's not like a major thing that people do. I guess I would know about it.
I think it was maybe a couple of slides before. You had a little paper.
This one?
Just very briefly, what does that mean? Green light visualization.
Oh, you're testing me now. I definitely have read this paper.
I can read the paper later, don't worry. I just thought.
I'm just going to quickly remind myself. Okay. Yeah, so in this case, what they've done, it's fluctuation driven. So what they've done is they've put it into a state which is typical in the brain, which is called this fluctuation-driven regime, where it produces a lot of spontaneous activity, but it's maximized for its sensitivity to transients. And that's this fluctuation. So it's fluctuations in the input that drive activity.
So they're adding these fluctuations to the website.
Well, yeah, so basically if you're imagining you've got some sort of like resting state, it's already producing a lot of activity. It's not set at zero, it's already producing lots of activity just randomly. And then if you add some extra input, it maximizes any extra input. Yep.
Any questions for the first part, for this part? I want to ask about this local learning. So what do you mean exactly? Because in the end, these neurons, when there's a structure, layers, so they get the spikes from their neighbors.
The non-local, yeah, so the feed-forward pass is local.
Yeah.
The non-local bit is that when you're computing these gradients,
Okay, so you're saying basically the vector propagation
is non-local, yes, because
Will be happening.
it couldn't be, right? It would need to, every neuron would need to know the state of every other neuron in the network, essentially.
I have a question about this thing. This comes from like happy and learning. The idea, the fact that you can also.
Yeah, so happy learning is an example of a local learning law, which is basically that if you have correlated inputs and outputs, you probably want to strengthen that connection. If they're uncorrelated, you weaken that connection. It definitely seems that the brain does do that, but that alone isn't enough to explain everything. Right, because neuroscience worked for a long time thinking that happy and learning could explain everything to learning. And it seems that the answer is that it doesn't. There's definitely more going on than that. But it is definitely a part of it. It's just that it doesn't get everywhere. You can do quite a lot actually, with just that. You can learn some simple things, but you can't just throw it at any data set and just magically learn to do it like by gradient descent.
Maybe also some words using machine learning to like growing neuronals.
Yeah, there are some things you can do. Yeah.
That's a bit expensive. It's easy.
Yeah, it's probably less expensive than doing full-on gradient descent spiking neurons. I guess.
But maybe, yeah.
Okay. No more questions, so let's thank them for
Yes, that's fine.